All right, hello everyone, good morning. Welcome to the second day of the summer school. It's my great pleasure to introduce our first speaker of the day, Sam Hopkins from MIT. Sam is an expert in anything at the intersection of statistics and algorithms, in particular algorithms for statistical problems. And today he will tell us about sum of squares hierarchy, which is a methods or collection of methods of how to obtain such algorithms. Take it away, Sam.
Thanks, Piotr. Okay, hi everyone. So today's lecture is about the sum of squares method, which is this. It's several things, and I'll talk about what it is, but it's a collection of methods for algorithm design that have been useful across theoretical computer science, optimization, and other fields, especially in the last 10 years or so. There's been a real boom of activity. I'm going to tell you about one particular point of view on using the sum of squares method to design algorithms for problems in high-dimensional statistics, focusing for today on one particular example, which is going to be the robust mean estimation problem. But first of all, if you ask 10 people what is sum of squares, you'll get sort of 10 different answers, and so I want to give you maybe 3 of those answers that are all really in harmony, but to try to give you a picture of a high-level picture of what it is. This is my first time doing this iPad in a live room thing. So do you see it if I do that? Yeah, that's cool. Okay. So the sum of squares method is a few things. One, at its most basic, it provides for every so-called semi-algebraic set in Rn. A semi-algebraic set is just the set of vectors in Rn such that some collection of multivariate polynomials with real coefficients are simultaneously non-negative at those vectors, at those points. So for any semi-algebraic set like this, it provides a hierarchy of convex relaxations, meaning convex sets that contain the base semi-algebraic set. So here is, some crazy non-convex set in red that I'm drawing as my semi-algebraic set. And then this hierarchy is indexed by a parameter called degree, and we usually write it as d, although in this talk, d is going to get confused between degree and dimension, and I apologize for that in advance. And when d equals 1, so it's an integer valued parameter, we have some relatively loose convex relaxation, although even the loose convex relaxation captures a lot of relaxations that are studied extensively in theoretical computer science, a lot of basic linear programming or semi-definite programming relaxations. And as you ratchet up the degree parameter, the relaxations become more computationally expensive to work with, but they get tighter and tighter until eventually, in the limit, the relaxation will be simply the convex hull of the underlying set. So the convex hull is the tightest possible convex relaxation. So you get a trade-off between relaxation quality and computational complexity, and I'll say a little later on, a little more quantitatively, what that trade-off looks like. Thing 2 that the sum of squares method is a proof system for reasoning about the tightness of those relaxations. So just because I provide you with a relaxation doesn't mean you know what it does. And we need some tools to mathematically reason about what you can do with the relaxations. And we're going to see later, actually, a lot of the lecture is going to focus on this proof system called the sum of squares proof system. Third is it's a set of philosophies for algorithm design. So this is not a formal thing. And you'll hear different philosophies from different people. And there are probably 3 or 4 philosophies, sort of methodologies or recipes for algorithm design that use these technical tools that have emerged in the last few years and have been extremely powerful. And the one I'm going to talk about today, lately in the literature, goes under the name proofs to algorithms. And it's a technique for doing something that sounds on the face of it magical, which is turning mathematical proofs written in a formal proof system in an automatic way into polynomial time algorithms for solving challenging computational problems. So this lecture is not really supposed to be all about a high-level overview of SOS, so I'm only going to just breeze through the extensive kind of applications that it's had, but over the last 10 or 15 years, we've seen applications in continuous optimization, combinatorial optimization, optimal control theory, quantum information, high-dimensional statistics, which is what I'm talking about today, cryptanalysis, and a lot more. So this is a very powerful algorithm design tool. Oh, I also want to say that because this is a summer school lecture and it would take forever to write out all the references, I'm just going to be very light on references. But I can, maybe Piotr can post things on the website. I can provide some notes that you can check with references to the literature. Okay, so let's get started. The plan is to illustrate the sum of squares method via an algorithm for a particular problem in high dimensional statistics called robust mean estimation. And this problem is perhaps the most basic problem in high dimensional robust statistics. Robust statistics is an area that has undergone a series of algorithmic breakthroughs over the last 5 years or so. Many of those breakthroughs involve the sum of squares method for algorithm design. The robust mean estimation actually was initially solved using another technique. And we're going to see a sum of squares based algorithm that was discovered later. But this is a particularly nice way, I think, to illustrate SOS. So what's the setup for robust mean estimation? By the way, you should feel free to interrupt me with questions. There's not, unless it gets out of hand. So for this talk, we will take capital D to be some distribution, some probability distribution on R little d. And so now I'm switching that little d is now dimension. By the way, is this font size okay? People in the back? It's okay. So distribution on R little d. And just for some notation, we're going to always have mu is some vector in RD, and it's the expectation of this distribution. So if I take a draw x from D and look at the expectation, that's mu. And I'm going to make an assumption about the covariance of this distribution. So the expectation over x drawn from D of the second moment matrix after I center by the mean, x minus mu transpose. So this is the covariance matrix of the distribution. This is some matrix that's D by D, and I'm going to assume that it is PSD at most the identity matrix, meaning its maximum eigenvalue is at most 1. And it's a covariance matrix, so its minimum eigenvalue is at least 0. It has eigenvalues bounded between 0 and 1. Now, what's the goal? Let's draw it with a picture. We're going to imagine that some samples, x1 through xn, have been drawn IID from D. And actually, I'm going to use the notation x1 prime to xn prime because we're about to have different x1 through xn's. And then those samples have been handed to a malicious adversary, an evil guy. And the malicious adversary gets to arbitrarily tamper with an epsilon fraction of them. So think of epsilon as like 1%. So 1% of the samples are maliciously tampered with. And then the adversary gives you back x1 through xn, of course, not telling you which samples she's messed with. And your goal, given these screwed up samples, is to, so given x1 through xn, estimate the true mean mu. That's the goal. Where by estimate, I mean just find some vector, which is close to mu in L2 distance. So, i.e. find mu hat such that mu hat minus mu is as small as possible. And we're going to have to see what as small as possible even means. So why study this model? This model dates back all the way to the 60s, actually, and it captures a few things. One is, of course, it captures the setup as described, that there's some actual adversarial contamination in samples and you want to do some useful statistics on them. But it also captures the possibility that the samples were drawn from a distribution that doesn't exactly fit your assumptions. So maybe those samples were drawn IID from some distribution, but it's a distribution that's only close to satisfying, say, this bounded covariance assumption, close in total variation distance. If that distribution is close in total variation distance, you can always model your samples as coming from this process. So this allows you to capture model misspecification or misspecified assumptions, as well as adversarial contamination. And of course, you can talk of this model is very generic, and you don't have to talk about mean estimation. You could talk about all kinds of other statistical tasks in this model. And the insights from studying robust mean estimation have turned out to transfer to algorithm design for a wide range of robust statistics problems. So our goal today is going to be to prove this theorem via the sum of squares method. Theorem. There exists a polynomial time algorithm which takes epsilon corrupted samples, x1 through xn, as long as n is at least some polynomial in d over epsilon. And with high probability, where this, for this talk, high probability means 99%, but you can make it as high as you want. With high probability, returns mu hat such that mu minus mu hat is less than O of square root of epsilon. Okay, that's the theorem. It turns out that square root of epsilon is the best you can do in an information theoretic sense, meaning even if I don't worry about polynomial time algorithms, it's possible to have two distributions which differ in total variation distance by only epsilon, and they both satisfy these assumptions, but their means are root epsilon apart. And under this model, you wouldn't be able to tell the difference between those two distributions, because I could take samples from one of them and then corrupt an epsilon fraction of them and make it look to you like you're getting samples from the other distribution. And that means that root epsilon is actually the best that you can do. I'm not going to construct those distributions for you. It's actually not hard to do because I want to focus on the algorithm design. But this is to say that this theorem is optimal up to the constant in front of the big O. Questions about this theorem statement? Okay. So before we get started on polynomial time algorithms, the actually first question we need to answer is, why is this possible at all? It's not obvious. Forget needing to run in polynomial time. Why should it be possible to find the mean of this distribution D if I give you epsilon corrupted samples up to this particular quantitative error root epsilon? In fact, maybe it's not even optimal, not even clear you can find it up to error polynomial in dimension. Who knows how much error the adversary can make you suffer? So let's prove, without worrying about polynomial time, that it's possible to identify the mean up to error root epsilon. Now, just to forecast what's coming, very often in high dimensional statistics, one proves some fact like I'm going to prove without worrying about polynomial time algorithms, and you prove it in a way that doesn't really lead you towards a polynomial time algorithm. And then you need to throw out all the work that you did, and yeah. Is it clear? No, I claimed it. You can't get order epsilon because there are two probability distributions. There exist two probability distributions whose means are separated by root epsilon, but which are total variation distance order epsilon. So the key fact about total variation distance that I'm using here, and I'll write it down a little bit later, is that if two distributions are separated in total variation distance by epsilon, then I can take a set of samples from one distribution and change an epsilon fraction of them and make it look like they came from the other distribution, make them distributed as though they came from the other distribution. Does that answer your question, right? Okay, so root epsilon is optimal.
Right, follow up on Rennie's question.
Yeah.
Is there some kind of natural assumption that you can make on the ability to corrupt these points, like some bounded covariance that would allow you to get the epsilon?
Nice question. I don't know about an assumption about the ability to corrupt the points. Bounded covariance actually would not do it. You can make stronger assumptions on the underlying distribution. So if you were to make the assumption that the underlying distribution was Gaussian, you could actually get order of epsilon. And there are even assumptions that allow you to interpolate between root epsilon and epsilon. But today we will just worry about the bounded covariance root epsilon case. But the ideas are actually more or less the same to get the other guarantees. Okay, good. These are great questions. Keep them coming. Others? What's the actual dependence? It's you can the proof I'm going to give is not going to give linear in D, but you can get linear in D. And you can, I mean, you can make a more refined. You can make more refined statements here where you get the success probability, you get the dependence of D of N on the success probability, and I'm not giving you the most refined. Oops, that was the wrong tool. Not giving you the most refined statement here, but you can get what you think you should. Great. Okay, so why is this possible? In statistics, we call why is this possible identifiability. Why can you identify the true mean up to error root epsilon given the corrupted samples? So actually, I want to prove this on a new page. So let's talk about identifiability. Okay, just the continuation of the point I wanted to make a moment ago. In high dimensional statistics or any statistics, often one proves identifiability in a way that doesn't yield a polynomial time algorithm, and then you forget all about everything you ever did and you work on algorithm design. The magic of the sum of squares method is that we will be able to take our proof of identifiability, cast it in a formal proof system, a formal mathematical language, and then in a totally black box way, obtain a polynomial time algorithm from that formal proof. We're going to start with a not formal proof. Formal means not formal in the sense that this proof will be in English and not in some restricted formal proof system. And then in the second half of these lectures, we're going to turn it into the kind of formal proof that we need to use the sum of squares method. Okay. So if there are no further questions, I want to prove why is it possible to identify the mean up to root epsilon. Let me first state a fact, and this is a basic fact about total variation distance. So if two distributions, let's say random variables, x and y, I'm going to be a little loose technically for total variation. I should talk about the distributions for these variables, but I'm just going to talk about total variation distance between random variables and hope that everyone's okay with my abusive notation. Have dTV, that's my notation for total variation distance, less than, let's use delta so that we don't confuse it with epsilon. Then there exists a coupling, meaning a way to sample these two random variables together as a joint distribution, xy, such that the probability that x equals y is at least 1 minus delta. So I can sample them together, and they will assume the same value almost all the time if delta is small. That's actually the meaning of total variation distance, or you can take this to be the meaning of total variation distance. So with this fact in hand, let's prove a lemma that's going to get us started on identifiability. Actually, this is basically all of the mathematical content. So let's let x and y be random variables on RD. So these guys assume, these are just probability distributions on RD. I'm just talking about them in random variable language. And let's assume that they both have bounded covariance. So meaning that I'm going to write out the definition of covariance just one more time here, and then I'm going to start using shorthand. And I'm just going to be a little loose with constants. Let's say it's order 1. So the maximum eigenvalue of the covariance matrix associated to x is constant as the dimension d goes to infinity, and the same for y. And let's assume that they have bounded total variation distance. So also DTV x and y is less than, actually, I'm going to go ahead and use epsilon here to hint what's coming later. Then their means are close. By root epsilon. So let's draw the picture. What's the picture look like? I'm going to draw the picture just in one dimension. If I have, I'm going to draw the PDFs of these guys. So I have, here's the PDF of X. And here's the PDF of Y. And actually here I've drawn them pretty far in total variation distance. Let's try to do a little better. So they're pretty close in total variation distance, meaning they have to overlap very heavily. They have to overlap heavily, and because they both have bounded variance, they're not allowed to have a lot of mass. Like X can't put a bunch of mass way out here, because that would kill this variance bound, right? So because X and Y are both not allowed to have too much mass away from the bulk of their mass, because of the variance bound, their means have to be close to sort of the bulk of their distributions, and therefore the means have to be close to each other because they overlap in their bulk. So this lemma just quantitatively captures that idea. Questions about the lemma statement? Okay, let's prove it. Oops, that's a big font size. Proof. So I'm going to take X and XY to be this optimal coupling between X and Y, right? This coupling that's described in the fact above. And now I'm just going to, I'm going to use this coupling to prove the lemma. So suppose I look at the square of the L2 distance between X and Y. So that's between the mean of X and the mean of Y. So in this picture, it's this distance here, if those are the two means. I'm just going to rewrite this as the inner product between two vectors. Expectation of X minus Y, where this expectation is over the joint distribution XY that are optimally coupled. The same vector. These are the same thing, just pushing the expectation around. Now, if I couple these two guys, X minus Y is 0 most of the time. It's only non-zero when the coupling fails. So let's focus on that event. That's really when something interesting is happening, is when the coupling fails. So this is actually equal to expectation of the indicator that the coupling fails times X minus Y. Right, when the coupling didn't fail, I got 0. Now I'm going to use the good old Cauchy-Schwarz inequality. Let me actually write one more step of this. I can use expectation. I'm going to pull this indicator out. And then expectation X minus expectation Y. So the notation's a little unfortunate here, but this expectation is associated to these copies of X and Y, and then we have just some fixed vector sitting over here. Now I'm going to use Cauchy-Schwarz. Expectation indicator coupling fails, squared, square root, times the square root of the other thing, squared, expectation of X minus Y, expectation X minus expectation Y. Okay, Cauchy-Schwarz. This is the only non-trivial inequality in this proof. And I want you to remember that. Good so far? Okay, we're almost there. So let's check in on what's happened. So I wanted to get a bound on this term. I wanted it to be small. The reason it was supposed to be small was that X and Y are close in total variation distance, and they have bounded variance. Look what I've got to show up. Here I've got something that's governed by the total variation distance between x and y, the probability that my coupling fails. Here I've got something, I haven't quite massaged it yet, but here I've got something that sure looks like a variance associated to x minus y, actually. I'm going to have to massage it a little bit to get it in terms of the variance in x and the variance of y. So both the things that I needed to show up, it's like Chekhov's gun, like we saw these assumptions, total variation and variance, and we've got our assumptions showing up now. This is good. So I'm going to go ahead and use the optimal coupling fact. So the indicator is its own square. So this is just the expectation of the indicator of an event. That's the probability of the event. And the probability of that event is at most epsilon. It's in a square root. So I'm just going to put root epsilon here. And then we're going to need to work on this second term. So square root of expectation x minus y, expectation x minus y, minus expectation y squared. Cool. Okay, so my last claim, I'm gonna go ahead and write this, and then we're gonna prove it. The claim is that this term, because it involves the variance of x and y, and we assumed that those guys had eigenvalues that were at most order 1, the claim is going to be that this is at most O of the norm of expectation x minus expectation y. And once I have that, I'm going to be done, because I'll just divide both sides. I've got the square of the norm here. I've got the norm here. Sorry, that gray is supposed to, I missed a root epsilon. I apologize. Times root epsilon. So when I divide both sides by the norm, I'm going to get that the norm is at most root epsilon, which is what I wanted. So I just need to establish this last inequality. So far, so good? Okay, so let's do that. So all I need to prove to show expectation of x minus y, and then actually I'm going to show this for any vector v squared is actually let's do it for the actual vector, expectation x minus expectation y squared. Actually, I'm really sorry. I lied to you slightly on the previous page. This is actually has a second term here, which is not really worth worrying about. It's got plus an epsilon times the square norm. But that does not going to matter, because I can just move this epsilon times this squared norm over here. I get 1 minus epsilon times the squared norm is less than the norm times root epsilon, which is good enough. Okay, so this is really what I need to show. So this is at most O of expectation x minus expectation y squared plus, let's hope I'm getting this right, well, let me just take, instead of writing out this whole thing, let's just upper bound this guy. Sorry for all of you writing in pen. Let's just upper bound this guy. So we're going to, we need to get this in terms of the variance of x and y. So to get the variance, we need to center our random variables x and y. So let's center them. Expectation, let's go x minus expectation x minus y minus expectation y. And then I need to recover from having centered them. So I put expectation x minus expectation y, expectation x minus expectation y squared. So I have a centered x, a centered y, and what's left over. Now I'm going to do Cauchy-Schwarz again. If I have the square of a sum of 3 things, I can bound that by some constant times the sum of the squares. O1 times expectation so that came from this term, x minus expectation x against expectation x minus expectation y, plus expectation y minus expectation y. So same thing for y. There's symmetry here. So everything we do for x, we really should be doing for y. And then plus expectation x minus expectation y, expectation x minus expectation y squared. And this big O goes around everything. Okay, so what do we have? This is the covariance matrix of X evaluated in this direction, right? Evaluated this vector. Because the covariance matrix of X has eigenvalues at most order 1, that means that when I evaluate the covariance matrix at this vector, I take the quadratic form, I get a number that it's at most order 1 times the square norm of that vector. Same goes for Y. Again, there's symmetry between X and Y. So that means that this guy is at most order 1 times the squared norm of expectation X minus expectation Y squared. Same goes here. And this last one, well, I've just got the inner product of expectation of X minus expectation Y with itself. So that's the square norm. And then I squared it again. So this last guy is just equal to expectation X minus expectation Y raised to the 4th. Okay. So now we've got essentially what we wanted. So let me just finish off the proof. Remember that we had this statement, and I lied slightly on where some epsilons went, and I apologize about that. But remember that we had this statement from this slide. I'm going to copy it down, that this guy was at most this. So I'm going to copy that down below. We had so the thing I wanted to bound was at most root epsilon times the square root of expectation X minus Y, expectation X minus expectation Y squared. And I just proved that this second thing, so now I got my big upper bound on the second term here. I got root epsilon. Let's put a big O so I don't have to worry anymore about that. Big O of root epsilon times expectation of X minus expectation Y plus expectation X minus expectation Y squared. So I had squared into the 4th up here, but I had a square root, right? Here I had square into the 4th, but I got a square root. And now life is good. I'm just going to rearrange. This tells me that 1 minus O of root epsilon times expectation X minus Y squared is at most O of root epsilon. I can divide now by the 1 minus O of root epsilon. I got what I wanted. Okay. I know that was a lot of inequalities. And I apologize for putting you to sleep so early in the morning. But let's wake back up. And remember that the high level point here was that I had two distributions. They had total variation distance close to 1. They had bounded variance, and that means their means have to be close. That's the statement of the lemma. And the proof of the lemma involved only 2 interesting steps. The first one was Cauchy-Schwarz, and the second one was just making use of these variance bounds. Those are the only 2 inequalities that I used. That's going to be important in the next hour when we figure out how to put this proof into a formal proof system. Okay, but I promised you a proof of identifiability. So now I need to use this lemma to tell you how to find the mean of a distribution from corrupted samples. The only other thing that I need to do this is a little lemma about concentration of measure, and this one's really just going to be an exercise. So, but here's a fact. Lemma 2. If I draw good samples, xn prime, from my distribution D, and remember I'm assuming bounded covariance, and I'm actually going to make an assumption here. I'm going to introduce an additional assumption. This assumption will also be in the theorem. It's not needed for the theorem statement. It's just making my life easier for today. I'm going to assume that D has bounded fourth moments. Just makes this little concentration lemma easier to prove. If x1 prime through xn prime are drawn from some distribution D with bounded covariance and fourth moments, and n is at least some polynomial in D over epsilon, then two concentration facts hold. First of all, the true mean of the distribution is close to the empirical mean of the samples. This expectation sub I notation means empirical mean averaged over samples. I is 1 through n. I can get it down to whatever function of epsilon I want here. And B, the empirical covariance is bounded. So if I average over samples, centered at the empirical mean, this is order 1. So this just says that the mean and covariance concentrate when I draw samples from a nice enough distribution. It's not too surprising. I'm not going to prove it here. You can do it as an exercise. But this gives us, if I put these lemmas together, I claim that this gives us an inefficient algorithm for finding the mean of a distribution from epsilon corrupted samples. So here's the, actually, let's draw a picture. So first, x1 through xn prime, these nice samples, get drawn, right? These are nice, xn prime. And then the adversary corrupts some of them. So maybe the adversary moves this one over here, and this one over here, and this one over here. And the adversary is sort of trying to pull the empirical mean maybe in this direction, right? Now, what I'm going to do is I'm going to take my corrupted samples and I'm going to try to find a collection of points in Rn whose empirical distribution, the average over those points, is 1 minus epsilon close in total variation distance to the corrupted samples that I get, and which has bounded empirical covariance. So basically, there's some distribution that's hidden from me. It's the empirical distribution over the good samples, x1 prime through xn prime. I get something that's epsilon close to it in TV distance. I'm going to try to find another thing that's epsilon close to that in TV distance, which has bounded covariance. So here I'm switching freely between population covariance and empirical covariance, right? I can talk about distributions like that are continuous, have continuous PDFs or something, or I can talk about distributions as the empirical distribution over a set of vectors. Why is that good for me? I just proved that if I find two distributions, if I have two distributions which are close in TV distance and both have bounded covariance, that their means will be close. So here's my inefficient algorithm. So I'm going to call it an algorithm in quotations because, I don't have a running time bound for this. Find, let's say y1 through yn in Rd such that the total variation distance between the empirical distribution on x1 through xn and y1 through yn is at most epsilon, and the empirical covariance of the y's, I'm just going to write this, covariance y1 through yn is bounded by order identity. And then output the empirical mean of the y's. Why should such a set of y's even exist? Well, the corrupted samples came from some good samples, right? The corrupted samples arose because the adversary corrupted an epsilon fraction of the good samples. And the good samples had bounded covariance. So one possible choice for these y's would be the good samples themselves. But by our lemma, so analysis, by the lemma, the mean of the y's minus the mean of the good samples, so these are two sets that have bounded covariance and they have total variation distance at most 2 epsilon by triangle inequality, is at most O over root epsilon. And by my concentration fact, I know that the mean of the y's is close to, the mean of the x primes is close to the vector I want. So now I just use triangle inequality and triangle inequality, and I'm done. Okay. That's identifiability for robust mean estimation. Yeah, nice question. Okay, Piotr says yes. The question was, what value of epsilon should we think of for this to make sense? You could think of epsilon, if you like, as something that is like a very small constant, like 0.01. Or if you want, you could think of it as something that's slowly going to 0, but maybe independently of the dimension. So what it's, how you shouldn't think of it, I guess, is as 1 over a polynomial in the number of samples. Like if epsilon is 1 over n, that's like saying the adversary only gets to corrupt 1 sample. That's a much less interesting problem. That's pretty easy to solve. So the problem becomes quite interesting when the adversary gets to corrupt a constant fraction of the samples. Even corrupting 1 over log n is quite interesting. So epsilon could be 1 over log n, and that becomes a hard problem. But if epsilon is like 1 over polynomial in n, it's maybe less interesting. Good question. Others? And then I promise we'll go back to sum of squares. We didn't actually talk about sum of squares, but the second half is going to be all about sum of squares.